Hi, good afternoon. I'm Haozhe. I'm from Advanced Robotics Center at NUS. So today I'll be presenting on Pegg-net, which stands for pixel-wise efficient graph generation in complex scenes. Okay, so a bit on the motivation for this project. So firstly, graph generation in robotics is a challenging problem that requires the ability to recognize and manipulate objects in complex and dynamic environments. And so these environments are often cluttered and contain moving objects, limiting the usefulness of existing models. And then in applications such as manufacturing and warehouse or household robotics, improving the graph success rate is critical for enhancing the efficiency and also cost reduction. Yeah. So to tackle these problems, we propose a novel architecture, which is Pegg-net, which is designed to specifically address the challenges posed by grasping in complex scenes and also dynamic scenarios. Okay, by improving the robustness and reliability of grasp generation in real-world environments, we can unlock a wide range of practical applications from improving productivity on manufacturing lines and also enabling more advanced domestic robots. Yeah. Okay, so for today's presentation, I'll be talking about three things. So firstly, I'll be talking about Pegg-net and its robotic grasping capabilities in complex scenes. Secondly, I'll be talking a bit about the live demo that we've had today, which demonstrates a potential use case for Pegg-net. And lastly, I'll talk a bit about the tangible benefits to the industry. Yeah. Okay. So this is the architecture of the Pegg-net grasping system. So Pegg-net is a planar grasp generation algorithm that takes in an RGBD image. So it takes in an RGBD image and predicts the optimal grasping point, the angle, and also the gripper width. So we have designed this network to be highly accurate and lightweight so as to guarantee the effectiveness and also the efficiency of grasping. This network only has about 1.4 million parameters. So it is one of the most lightweight models designed for planar grasping. Yeah. Okay. So since Pegg-net is small, it's lightweight and efficient, it can make grasp pose predictions in real time. So if we integrate Pegg-net with a closed-loop control system that is guided by position-based visual servoing, then we are able to obtain a grasping system that can grasp dynamic objects. Yeah, and then this robotic grasping system can operate at dynamic conditions of up to 50 Hertz. Yes. Okay, so I've prepared a video that showcases some of Pegg-net's grasping capabilities in complex scenes. Oh, the video has no problem. Oh, okay. Then it's okay because the video is actually available on YouTube, and if you scan the link at our post, scan the QR code on our poster, you can actually access the video. So I'll skip this video then. Huh? Oh, but there's no sound though. Okay. Then. Okay, let's see it. Yeah, I'll explain a bit along the way then. You can fast forward a bit. There's some narration in front actually, but okay. Let me just can so yeah, here we are actually placing objects one by one, so into a complex scene. So we're showing how Pegg-net is able to focus on only the graspable objects in the scene. It's actually ignoring the background. So even though the RGB image actually captures the background, it actually doesn't affect the predictions. And then in this case, we're looking at grasping in dynamic environments. So as Pegg-net is moving down to grasp the object, we can move the objects in the surroundings, and the Pegg-net will follow. So the Pegg-net will follow the object to its new grasping position. So it's actually making the inference in real time, and it's able to track the objects. Yeah. It's not letting me forward. Yeah. Oh, never mind. Yeah, but the last one is actually us. Last one actually showcases a demonstration of how Pegg-net is able to grasp different types of objects. So mainly household and warehouse objects from a cluttered scene. Yeah. So I'll skip this part then, since I can't fast forward. Yeah, I can show it in the demo outside. Yeah. Okay, so now I'll talk a bit about the workshop live demo. Yeah. So for this workshop live demo, actually what we've come up with is okay. Yeah, so as I talked about in my earlier in my presentation, so the grasping of okay, the grasping of unknown objects is an important manipulation capability that's required for industrial robots and service applications. So using NVIDIA Isaac Sim, we actually created a realistic simulation environment to allow us to test how well the robotic grasping system can perform in simulation before we actually deploy it out into the real world. Because actually deploying an algorithm that has not been fully tested before on a physical robot can actually be dangerous when it fails. So what we want to do first is, can we find a way to be able to realistically test and simulate how it will perform in the real world before we actually deploy it on a physical robot. So in the video on the right here, what we're actually showing is Pegg-net running in simulation. So we're showing how Pegg-net can grasp objects of adversarial geometry in simulation. Yeah. Okay. Okay. So on top of Isaac Sim, we actually utilize another tool called NVIDIA Isaac Cortex. And what Isaac Cortex allows us to do is that it allows us to synchronize the motions of the physical and the virtual robot. So Isaac Cortex can make decisions on how to move move the virtual robot in simulation, and then this motion can be synchronized to the physical robot, such that the physical robot will be able to mimic that same motion in the real world. So the advantage of doing this is that it allows us to be able to first test out a grasping system in simulation, and then using that same code replicate that same process, the same grasping and manipulation process in the real world using a real robot. Yeah. So in this demo, we're demonstrating how we can control the physical robot using the simulation environment. So it's actually very simple. So what we do is we actually just use a mouse to drag the end effector in the simulation, and then the physical robot will move exactly like how the virtual robot would in simulation. Okay. And then the second demonstration here is that we're using the real robot to replicate a simulation task. So so in simulation, what's happening right now is the virtual robot is actually performing a block stacking task, and then this task is actually also performed by the physical robot at the same time on a physical setup that we have in the lab. Yeah. Okay, so now I'll talk a bit about how we can deploy Pegg-net using the same concept as well. So for the two demonstrations I showed just now, it does not require input from the real world. So it's purely something that happens in simulation, and then the resulting actuations are actually actually channeled, and their commands are published to the real robot, and the robot moves in accordingly. But the difference that Pegg-net brings is Pegg-net requires real data from the real world in order to make its predictions and also execute grasps. So which is the RGBD data. So what we're doing here is we need the real world data, real world perception data, to be streamed into Isaac Cortex, in which Pegg-net will run. And then based on the prediction of Pegg-net, Isaac Cortex will make decision as to where to Isaac Cortex will make the decision as to where to move the end effector so that you can grasp the object. And then that command will then be published to the physical robot, and the physical robot will move to that position to actually execute the grasp. Yeah. And then this is the result, which is the demo that we're showing outside. So the real world grasping is that this is the picture of the real world grasping, and then this is what's happening in simulation. So the RGBD images are being streamed into Isaac Cortex, and then Pegg-net will make a prediction based on this RGBD image, and then it will tell the robot in simulation where to move to in order to execute that grasp. And then this information is also published to the physical robot, which will actually execute the grasp in the real world. Yeah. Okay. So now I'll talk a bit about the tangible benefits to the industry. So what can this synchronized sim to real platform do for the industry? So I think there are 5 main ways that the industry can benefit from this. So firstly is reduce cost. So traditional methods of developing robotic grasping and manipulation systems require expensive hardware and also time-consuming trial and error testing, which also requires a large amount of data. And having a synchronized sim to real platform can allow for much of this testing and also data collection to be done virtually, and which reduces cost and also increases efficiency. And then secondly is to improve efficiency, and then thirdly is also very safe. So the use of a simulation environment can provide a safe method of testing robotic grasping and simulation algorithms, which can reduce the risk of damaging the expensive hardware and also injury to human operators. Because if your software is unstable, testing it on a physical robot directly may cause harm to human operators. Yeah. And then next is enhanced performance. So the ability to test and optimize an algorithm in simulation allows developers to achieve higher levels of accuracy and also performance in robotic grasping, leading to more effective and reliable systems. Okay. Lastly is better scalability. So having such a platform can also facilitate the development of more scalable robotic grasping and manipulation systems. So you can test a lot of different systems at the same time. And then and you can refine them in simulation before actually deploying them in the real world. Okay, so overall, having a sim to real platform for robotic grasping and manipulation has the potential to significantly improve the efficiency, safety, and performance of industrial robotic systems, which leads to greater productivity and cost savings for companies. Yeah. So in conclusion, so for my presentation today, I've talked about Pegg-net and its grasping capabilities in complex scenes. I've demonstrated a potential use case for Pegg-net and also possibly other types of grasping algorithms that can make use of this concept of first testing it out in simulation and then directly deploying it seamlessly onto a physical robot, and also discuss some tangible benefits that such a platform might have to the industry. Thank you.
Any questions from Mr. Wang?
Hi. Yeah. Right. Yeah. Right. Yes. Mm. Mm. I think it's possible. I think it's possible. Yeah. Because we are able to actually get a lot more information from the real world. So right now, so for example, in the cortex diagram that I drew just now, the only thing that's getting streamed back into the simulation environment is the perception data. But with the real robot, I am able to get also force sensors, torque sensors. Yeah. And then all this data can be combined to actually help me to train the model better. So I think that it is possible for us to actually use this platform to actually acquire data. So yes. Yeah. Sure. Okay. This one? Okay. Uh, no, this mm, we are executing, we're moving the end effector of the virtual robot to the position where it can grasp the object. It's simultaneously, but this is only when I'll do this is only when I've tested first using the simulation only environment that the algorithm is stable. Yeah, correct. So what I've done first is I'll go back a few more slides. So what I've done first is actually here. This is running in simulation only. Yeah. So I test here, make sure that the algorithm is stable, and then I'll move forward to actually do the synchronization with the physical robot. And then over here, the real world, sorry, not this one. The real world perception data gets streamed in instead of the perception data from the simulation environment. And then using the perception data from the real world, I pass it to Pegg-net, and Pegg-net makes a decision. And then the virtual robot arm moves. Yes, it's working in the simulation. Yes. Yeah. Okay. Sorry, I didn't make it accurate. Yeah. Okay. Hi. Processor, you mean GPU, CPU? Oh, you mean to run the software or to run Pegnet? Oh, to run Isaac Sim, actually, it's pretty computationally intensive. So we've tried using a 3090 to run Isaac Sim is possible. But for today's live demo, we actually use a 4090 so that we could run both Isaac Sim and Pegnet together on the environment. But mainly the computationally intensive part is running the simulation and not running the model itself. So the model itself doesn't actually require too much computational resources. A very normal GPU would work, but running the simulation environment together with the model requires quite a bit of computational power. Yeah, mainly because the rendering is uses up a lot of the GPU capacity. Yeah, in order to make the rendering realistic, a lot of GPU computational power is needed. Yeah. Hi. Yeah. Mm. Yes. Oh, and also the pose and yeah. Yes. Yeah. Mm. Okay. I understand your question. Okay. So for Pegnet right now, it is a planar grasping algorithm. So we don't consider picking from the side yet. But the same concept over here can apply for a different algorithm. So we can substitute Pegnet with something else. And the same flowchart would work. So for example, let's substitute Pegnet with a 6DOF grasping algorithm that allows us to be able to grasp from the side and stuff. So that same algorithm will make a prediction based on the input images from the real world. It will decide on the grasping position and also the pose of the end effector. That information will be given to the robot in virtual robot. The virtual robot will move, and then the real robot will move together with it. Yeah. Not another Pegnet, but another 6DOF grasping network. Because Pegnet is 4DOF grasping, so it's yes. So Pegnet will yes. Yeah. So the network will first predict the optimal grasping point. So the location first. The location gets predicted first. And then based on that location, it will select only one host. So only one gripper orientation, also only one gripper width. Yeah. It won't output all of the gripper widths, even though you are right in saying that there can be infinitely many. Yeah. It's based on the network prediction. Yes, based on network prediction. So the network will only predict one grasp per object. It won't predict multiple grasps for all object. Yeah. Oh, it's according to the probability of grasping success. So it looks for the grasping position or with the highest probability of grasping success. And then it fixes that position first. And then at that position, what should the gripper orientation be and what should gripper width be? And then it will execute based on that. So it predicts three things. Yeah. Yes. Um. Mm, 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 mm. Yes, I think so. Yeah. So the gripper is unless you substitute with a very small gripper or gripper that size is significantly different from like other grippers, then maybe you have a problem. But largely, I think right now, because in the first demo we were using the Kinova gripper, and then for this demo we're using the Franca gripper. So from the Kinova gripper to the Franca gripper, we did not actually experience too many issues due to the gripper change. So I think is largely okay because the model is not too robot dependent. But I guess if the gripper size or the shape of the gripper differs a lot from the parallel sort of configuration, then it may affect. Yeah. No, it's not passed in the Pegg-net. So Pegg-net assumes that you have a parallel plate gripper, but what size that gripper is, Pegg-net actually doesn't know. So sort of, I would say that in a general sense, you may have to tune the algorithm sort of to sort of compensate for the gripper. Maybe that needs to be done, but may not always be necessary. It depends on how much, so sort of how much the gripper actually affects the graph. Yeah, this one has to be tested actually. Yeah. Hi. Right, yes. No, we did not collect the data from this simulation, but the data that we trained on was synthetic data. So we trained Pegg-net on the Jacket dataset. And the Jacket dataset consists of objects from ShapeNet. So that is actually synthetic data. It's not real world data. So in a sense, we did train on a synthetic dataset, but the synthetic dataset was not collected in this simulation environment. Yeah. So running an algorithm that we've developed first in the simulation world allows us to safely test the algorithm to see whether it's stable first. Yeah. So before we actually run the algorithm in the real world, we want to make sure that the gripper doesn't collide with sort of the robot arm doesn't do anything funny. It doesn't collide with any surface. It doesn't hurt the humans or whatever. So we test it out in simulation first. So in the beginning, this synchronization doesn't happen. We test it out to make sure that it's stable first, and then we do the synchronization. Yeah. 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 Okay. Thank you.
Thank you, Mr. Wang.